Welcome to today's session. In this video, we'll be exploring an interesting problem from LeetCode, number 959, regions cut by slashes. This problem challenges us to analyze a grid divided by slashes and determine the number of connected regions formed. Stay tuned as we break down the problem and dive into efficient solutions. In this problem, we are given an n-by-n grid, where each cell contains one of three possible characters: a blank space, a forward slash, or a backslash. The grid initially represents one connected area of empty space. However, the slashes divide the cells diagonally, forward slashes split a cell from the top left corner to the bottom right, and backslashes split it from the top right corner to the bottom left. Your goal is to figure out how many distinct regions of empty space are formed after accounting for these divisions. A region is defined as any connected area of empty space that is not interrupted by slashes. The output of this problem is an integer representing the total number of regions formed. To clarify this with an example, consider the grid, forward slash. This is a 2x2 grid where the first cell contains a forward slash, and the second row starts with another forward slash. When visualized, the grid looks like this. The top left cell has a diagonal from top left to bottom right, and the bottom left cell has a similar diagonal. These slashes divide the space into two separate regions. After dividing the cells based on the slashes, you can see that the first cell in the top left is split into two regions by the forward slash. Similarly, the bottom left cell is also split into two regions. When we count all the connected regions of empty space across the grid, we find that there are exactly two distinct regions. Now, let's take a look at another example. For the grid, forward slash, we have a similar 2x2 configuration, but the second row is entirely empty space. In this case, the top left cell is divided into two parts by the forward slash. However, since there are no other slashes or divisions in the bottom row, the entire grid remains connected as one single region. Even though the slash splits the top left cell, both parts of the slash still belong to the same connected area of empty space. Therefore, the output for this example is one distinct region. Now, consider another example where the grid is forward slash backslash. This time, we have a mix of backslashes and forward slashes. In this grid, each cell is divided into multiple regions by the slashes and backslashes. For instance, the top left cell contains a backslash and forward slash, which creates separate disconnected regions within that cell. Similarly, the bottom right cell is also divided by slashes. When you count all the separate regions formed across the entire grid, you find that there are four distinct regions. This demonstrates how the arrangement of slashes and backslashes can lead to varying numbers of regions. To help you solve this problem, here are some important constraints to keep in mind. The grid is always an n by n square, where n ranges from 1 to 30. Each cell contains exactly one of the three characters: a blank space, a forward slash, or a backslash. The maximum number of regions for a grid can be calculated as 4 times n squared, which accounts for the scenario where every cell is divided into 4 parts. As an edge case, when the grid contains no slashes, the entire grid remains one connected region. On the other hand, if every cell contains a slash, the number of regions is maximized. Understanding these constraints will help you design an efficient solution for the problem. To solve the problem regions cut by slashes, we need to determine the number of connected regions in a grid where each cell is divided by slashes, represented as forward slash and backslash. Each of these slashes splits a square cell into triangular regions, creating a graph-like structure. The challenge lies in identifying and counting the connected components formed by these triangular divisions. One straightforward approach is to divide each square cell into 4 smaller triangular regions: top, bottom, left, and right. These triangles can then be treated as graph nodes. Within the same cell, connections between these nodes depend on the type of slash present. For example, a forward slash connects specific pairs of triangles, while a backslash connects others. Beyond the cell boundary, triangles in adjacent cells are merged if their edges align. Once this graph structure is complete, we can use a traversal technique like depth-first search, DFS, or union find to count the connected components. However, while this brute force method is simple and intuitive, it increases the grid size significantly. Each square is essentially divided into 4 nodes, resulting in n squared nodes, where n is the grid dimension. The graph traversal itself adds an additional O, n squared, complexity, making the overall approach quadratic in nature. This rise in memory usage and computational load presents certain drawbacks, which we'll now address by considering alternative strategies. One significant drawback of the brute force approach is its high memory usage, as it explicitly subdivides each cell into 4 nodes. To address this, we can use an optimized union-find approach that avoids creating these subdivisions. Instead of representing each triangle explicitly, we track their relationships implicitly. Here, each triangular region is assigned a unique identifier, and we use the union-find data structure to merge regions based on their connections. Within each cell, the presence of slashes implicitly determines which regions are connected. For instance, a forward slash or backslash dictates how regions are merged inside the cell. Additionally, edges shared between adjacent cells guide the merging of regions across cell boundaries. Once we've processed the entire grid, the number of disjoint sets in the union-find structure corresponds to the number of connected regions. The computational complexity of this method is O, n squared asterisk alpha, n, where alpha, n, is the inverse Ackermann function, a factor that grows extremely slowly. This means the number of operations is effectively proportional to the number of cells in the grid. The primary advantage here is memory efficiency. By avoiding the explicit subdivision of cells, we significantly reduce overhead, making this approach far more suitable for larger grids. Another approach is to use depth-first search, or DFS, directly on the implicit graph created by the slashes in the grid. Instead of subdividing cells or explicitly tracking regions, we treat the slashes as edges in the graph. Each connected region corresponds to a component in this graph. To implement this, we traverse the grid, marking regions as visited during the DFS traversal. Every time we initiate a new DFS call, it signifies discovering a new connected region. The number of DFS calls ultimately gives the count of connected components. This method has a time complexity of O, n squared, similar to UnionFind. However, handling edge cases, such as ambiguous connections at cell boundaries, requires careful implementation and can make this approach more error-prone. For problems involving larger grids, these edge cases can become cumbersome, which is why we lean towards a solution that is not only efficient but also easier to manage. Based on these considerations, we arrive at the final choice for our strategy. The chosen strategy leverages the optimized UnionFind approach without explicit subdivision, as it strikes the right balance between efficiency and simplicity. One key insight is recognizing that while each square cell can theoretically be divided into 4 regions, we don't need to create these regions explicitly. UnionFind allows us to track connections between regions implicitly, making the solution both memory efficient and scalable. The slashes in the grid act as constraints, determining whether regions within a cell or between adjacent cells are connected or separate. The number of connected components in the UnionFind structure directly corresponds to the number of independent regions in the grid. Comparing the approaches, the brute force method is intuitive but memory-intensive and less scalable. DFS is effective but has implementation challenges, particularly with edge cases in larger grids. UnionFind, on the other hand, combines efficiency, scalability, and clarity, making it an optimal choice for this problem. This method is not only well-suited to handle large grids but also offers straightforward logic for merging regions, ensuring the solution is elegant and robust. To solve the problem regions cut by slashes, we start by understanding how slashes divide the grid and how they affect the structure of each cell. Each cell in the grid is represented as a square, and when a slash or backslash is present, it divides the square into triangular regions. For example, a forward slash divides the square into 2 triangles, one in the top left corner and the other in the bottom right. Similarly, a backslash divides it into 2 triangles, one in the top right corner and the other in the bottom left. This means that for every cell, slashes create subdivisions that we need to analyze for connectivity. To simplify the problem, we treat each cell as if it's divided into 4 smaller triangular regions, numbered as 0, 1, 2, and 3. Region 0 represents the top left part of the cell, Region 1 the top right, Region 2 the bottom right, and Region 3 the bottom left. This subdivision is the foundation for building our solution. Now, based on the character in the cell, these 4 regions are connected in specific ways. A forward slash connects region 0 with region 1 and region 2 with region 3, forming two separate pairs. A backslash, on the other hand, connects region 0 with region 3 and region 1 with region 2, pairing diagonally opposite regions. If the cell contains a space, all four regions within the cell are connected. With this understanding, we can now build a graph where these triangular regions are the nodes, and their connections are the edges. To manage these connections efficiently, we use a disjoint set union, also known as union find. This data structure is ideal for tracking which regions belong to the same connected component. We start by connecting regions within each cell based on its character. Then, we extend these connections to adjacent cells. For example, the bottom edge of one cell connects to the top edge of the cell directly below, and the right edge connects to the left edge of the cell to its right. This ensures that connectivity is maintained across the entire grid. Once we've set up these connections, the next step is to count the number of connected components. Each connected component represents a distinct region in the grid. The union find data structure makes this process efficient. It allows us to quickly merge regions with the union operation and determine their root with the find operation. One of the key insights here is that subdividing each cell into four regions simplifies the problem by reducing it to managing connections between these smaller parts. The union find structure is particularly efficient due to optimizations like path compression and union by rank, which keep the operations fast. Properly handling edge connectivity between adjacent cells is crucial, as any missed connection would lead to an inaccurate count of regions. In terms of space complexity, the memory usage grows with the number of regions, which is proportional to 4 times the total number of cells. For typical grid sizes, such as 30 by 30, this is manageable. By combining these insights, we can solve the problem both accurately and efficiently. In the implementation, we start by initializing the union find structure for all the regions in the grid. Since each cell is divided into 4 regions, a grid of size n by n will have 4 times n squared regions in total. Next, we process each cell in the grid. For every cell, we connect its internal regions based on whether it contains a forward slash, a backslash, or a space. Then, we connect the regions on its edges to the corresponding regions in adjacent cells. Finally, after processing all the cells, we count the number of unique roots in the union find structure. Each unique root represents a connected component, which corresponds to one distinct region in the grid. The time complexity of this solution is approximately O(n squared, multiplied by the inverse Ackermann function, which is close to constant in practical scenarios. This efficiency comes from the nearly constant time complexity of union find operations. The space complexity of our approach is O(n squared, because we store the union find structure for all the regions in the grid. To see this algorithm in action, let's consider an example. Suppose the input grid looks like this: a forward slash in the top left, a backslash in the top right, and other slashes and spaces distributed throughout. We subdivide each cell into regions and use union find to connect them based on the cell's content and adjacency. After processing the entire grid, we count the number of unique connected components. In this example, the grid results in 6 distinct regions. This demonstrates how the algorithm systematically counts regions by managing connections and efficiently tracking components using union find. Here, we begin by defining a class called solution and implementing the regions by slashes method. The input to this method is a grid, which represents the slashes and spaces in a square grid. First, we determine the size of the grid, n, and initialize an empty dictionary called parent, which will later be used for the union find data structure. Next, 2 helper functions, find and union, are defined. The find function identifies the root of a given region using path compression to optimize the process, ensuring that subsequent lookups for the same region are faster. The union function merges 2 regions by linking their roots, ensuring that they belong to the same connected component. After this, we conceptualize each cell in the grid as being divided into 4 regions: top, right, bottom, and left, which are labeled as 0, 1, 2, and 3 respectively. For every cell in the grid, these regions are represented as tuples containing the cell coordinates and the region label. The next step is to initialize the parent pointers for each of these 4 regions within the cell. For example, the top region of the cell at position i, j, is set to point to itself initially, and the same is done for the other 3 regions. Following this, we establish connections between adjacent cells in the grid. If the current cell is not in the first row, we connect its top region with the bottom region of the cell above it. Similarly, if the current cell is not in the first column, we connect its left region with the right region of the cell to its left. These connections ensure that adjacent cells properly share their boundaries. After setting up these base connections, we process the slashes within the grid. When a forward slash is encountered, we connect the top region with the left region and the bottom region with the right region of the current cell. For a backslash, we connect the top region with the right region and the bottom region with the left region. This setup ensures that the boundaries created by slashes are correctly modeled. For cells that are empty, meaning they contain a space, all four regions within the cell are connected together. This is done by uniting the top, right, bottom, and left regions, effectively treating the cell as a single region without any internal divisions. Once all cells have been processed and all relevant unions have been performed, the next step is to determine the number of unique regions in the grid. To do this, we use the find function to identify the root of each region and then count the distinct roots within the parent dictionary. Each unique root corresponds to a distinct region in the grid. Finally, the method returns the total count of these unique regions, which represents the solution to the problem. Here, we start by importing necessary utilities and defining the solution class. Within it, we implement the regions by slashes method, which takes a grid of strings as input. First, we determine the size of the grid and initialize a parent map to manage the disjoint set data structure. This map helps us represent connected regions in the grid. Next, we define two helper functions, find and union. The find function retrieves the root of a node with path compression to optimize performance. This ensures that all nodes in a connected region point directly to their root. The union function merges two regions by connecting their roots. This forms the backbone of our approach to determine the number of distinct regions. Then, we begin initializing regions for each cell in the grid. Each cell is divided into four parts, representing its top, right, bottom, and left segments. For each cell, we construct unique keys for its four segments, top, right, bottom, and left. These keys use the cell's coordinates combined with a segment identifier. We add these keys to the parent map, setting each segment as its own root initially. After initializing the segments, we connect adjacent cells wherever appropriate. If the current cell has a cell above it, we connect the top segment of the current cell to the bottom segment of the cell above. Similarly, if the current cell has a cell to its left, we connect the left segment of the current cell to the right segment of the cell on the left. This ensures that shared boundaries between cells are represented as connected regions. Now, we move on to processing the slashes within the grid. For each cell, we check the character at its position. If it contains a forward slash, we connect the top segment to the left and the right segment to the bottom, effectively dividing the cell diagonally. If the cell contains a backslash, we connect the top segment to the right and the bottom segment to the left, dividing the cell diagonally in the opposite direction. If the cell is empty, we connect all four segments together, treating the cell as a single unified region. After processing the entire grid, we count the number of unique regions by finding the distinct roots in the parent map. We use a hash set to store these unique roots, as each root represents a separate region. Finally, we return the size of this set, which gives the total number of distinct regions in the grid. This implementation efficiently handles the problem by leveraging the union find algorithm to manage connected components and resolve overlaps created by slashes. The result is a robust solution that scales well with the size of the grid. To solve this problem, we start by dividing each cell in the grid into four triangular regions, corresponding to the top, right, bottom, and left. For the given input grid of size 2x2, this results in 16 unique regions, and we initialize each as its own parent in the union find data structure. Next, we handle the connections between adjacent cells. For example, the bottom region of cell 0, 0 connects to the top region of cell 1, 0, and the right region of cell 0, 0 connects to the left region of cell 0, 1. This ensures that regions across adjacent cells are properly linked. Now, we need to account for the slashes within each cell. A forward slash splits the cell diagonally from the top left to the bottom right, so we connect the top region with the left region and the bottom region with the right. This setup lays the foundation for counting distinct regions in the grid. In the 2x2 grid example, we continue processing the slashes. For cell 00, which contains a forward slash, we connect its top region with its left region and its bottom region with its right region to reflect the diagonal division. Similarly, for cell 11, which contains a backslash, we connect the top region with the right region and the bottom region with the left region. Once all slashes are processed, the next step is to count the distinct regions. Using the union find structure, we identify all unique root representatives in the parent dictionary. Each distinct root corresponds to a separate region in the grid. For this example, there are 5 distinct regions, so the output is 5. Now let's look at a larger grid where all cells are empty. The input grid is 2 times 2, and as before, we divide each cell into 4 triangular regions and initialize the union find structure. Since there are no slashes, we perform union operations to merge all 4 regions within each cell. For instance, in cell 00, we union the top region with the right with the bottom, and the bottom with the left, effectively treating the entire cell as a single region. Additionally, we connect adjacent cells by merging their respective boundary regions, such as the bottom of 00 with the top of 10 and the right of 00 with the left of 01. After completing these union operations, the entire grid becomes one connected region. Using the union find structure, we count the unique root representatives, which is just 1, and that's the output. Finally, we examine a more complex grid with mixed slashes. The input grid is 2 times 2, and as usual, we divide each cell into 4 triangular regions and initialize the union find structure. We then proceed to connect adjacent cells along their shared boundaries. Next, we account for the slashes within the grid. For cell 00, which contains a backslash, we connect its top region with its right and its bottom with its left. Cell 01 contains a forward slash, so we connect its top region with its left and its bottom with its right. We repeat this process for the remaining cells, ensuring that each slash is properly represented in the union find structure. After processing all connections and slashes, we count the distinct root representatives in the parent dictionary. In this example, there are 4 unique regions, so the output is 4. The time complexity of our solution can be analyzed in 3 main steps. First, we initialize the parent pointers for the union find data structure. Since each cell in the grid is divided into 4 regions and there are n squared cells in total, this results in 4 n squared regions to initialize. This process is straightforward and takes n squared time. Next, we perform union find operations for each cell. These operations include connecting regions within the cell as well as regions across adjacent cells. For adjacent cells, we perform at most 2 union operations for each pair of vertical and horizontal neighbors, which scales to n squared for the entire grid. Additionally, handling the slashes and empty spaces within each cell involves 2 to 4 union operations per cell, which also totals n squared operations across the grid. Importantly, each union and find operation has an amortized time complexity of alpha v, where alpha is the inverse Ackermann function. Since this function grows extremely slowly and is nearly constant for practical input sizes, the time complexity of these operations effectively remains n squared when considering all regions together. After initializing the parent pointers and performing the union find operations, the final step is to count the number of unique regions in the grid. To do this, we iterate through all 4 n squared regions and apply the find operation to determine each region's representative parent. Similar to the union operations, each find operation has an amortized complexity of alpha v, making this step n squared in practice. Combining all these steps, the overall time complexity of the solution is dominated by the union find operations, resulting in a total time complexity of n squared. For the space complexity, the main factor is the storage of the parent dictionary. This dictionary maps each of the 4 n squared regions to their respective parent, requiring n squared space. Additionally, the find function uses recursion for path compression, but thanks to the efficiency of the union find algorithm, the recursion depth is minimal, effectively 1, due to the near constant growth of the union find tree height. As a result, the space complexity remains n squared. In summary, the overall space complexity of the solution is O(n squared). Now let's analyze the best, average, and worst cases for time complexity. In the best case, where the grid is completely empty, all cells are blank spaces, all the regions within a cell are immediately unioned. However, even in this case, we still need to iterate over all cells and perform union find operations, resulting in O(n squared) complexity. In the worst case, the grid contains an alternating pattern of / and /, creating more distinct regions. Despite this increase in distinct regions, the union find operations still remain O(n squared) due to the efficiency of the amortized O, alpha, v, complexity. For the average case, the complexity is similar to the worst case because the dominating factor remains the grid size rather than its specific content. When compared to a brute force approach, which would explicitly simulate regions using techniques like DFS or BFS, union find significantly outperforms. A naive method could require O(n squared) space for the simulation and O(n squared) time per DFS or BFS operation, resulting in a total time complexity of O(n to the power of 4). In contrast, union find avoids explicit region simulation and achieves O(n squared) efficiency. To understand why the complexity is O(n squared), we can break it down mathematically. The grid consists of n squared cells, and each cell is divided into 4 regions, resulting in 4*n squared regions overall. The union find operations on these regions have an amortized time complexity of O, alpha, v, per operation, and there are O(n squared) operations in total. This leads to a combined time complexity of O(n squared). The inverse Ackermann function, alpha v, grows so slowly that it is practically constant for all reasonable input sizes, which is why the union find approach is incredibly efficient. This efficiency highlights the strength of the algorithm, making it suitable for solving problems of this nature within a manageable time frame and space usage, even for larger grids. Overall, the solution's O(n squared) complexity ensures scalability and demonstrates the power of mathematical reasoning and algorithmic optimization in handling grid-based problems like this one. One common mistake is confusing grid cells with graph nodes. When a slash, whether / or /, is present in a grid cell, it splits the square into multiple triangular regions. If we treat the entire cell as a single node without considering this division, we fail to capture the finer structure of the problem. Each square should actually be represented by 4 smaller triangles, making this distinction critical. Another issue arises with incorrect union find implementations. If components are not properly initialized or connected, cycles can form, or connected regions may fail to merge, both of which lead to incorrect region counts. Additionally, overlooking boundaries between adjacent cells is another frequent error. Triangles on opposite sides of a cell boundary must be connected when they belong to the same region. Otherwise, regions spanning multiple cells will be mistakenly counted as separate, leading to undercounting of the total regions. Another common issue is inefficient traversal during DFS or BFS. Forgetting to check whether a triangle has already been visited or using redundant loops means these algorithms revisit the same nodes unnecessarily. This increases the time complexity and can slow down the solution significantly, especially for large grids. Misinterpreting the orientation of / and / is also problematic. These slashes divide the square differently, with / typically creating a top left to bottom right split, while / forms a bottom left to top right split. Misunderstanding these orientations can result in incorrect adjacency relationships, which in turn leads to errors in identifying connected regions. A key insight for this problem is to represent each grid cell as 4 distinct triangles. Structuring the problem this way allows you to model the grid as a graph, where each triangle represents a node. This makes it easier to apply algorithms like union find or DFS and BFS. Between these, union find is often faster because it efficiently merges regions and avoids the need for exhaustive traversal. When preparing for interviews, consider edge cases such as grids that are completely empty, completely filled, contain no slashes, or have alternating / and / patterns. Optimizing your union find implementation with path compression and union by rank can significantly improve performance, bringing the time complexity per operation close to constant. Additionally, practicing related problems like most stones removed with same row or column, number of islands, and number of closed islands can strengthen your understanding of graph and connectivity problems. One alternative approach is the grid expansion method. In this technique, each cell is expanded into a 3x3 grid, and slashes are mapped to specific smaller cells within this expanded grid. BFS or DFS can then be used to count the regions. This approach is easier to visualize and implement, but it comes at the cost of increased space complexity, growing to O, open parenthesis n times 3 close parenthesis squared. Another option is union find with the triangle representation. Here, each cell is broken into 4 triangles, and the union find algorithm is applied to merge these triangles into connected regions. While this method is more abstract and requires careful implementation, it is highly space efficient and computationally optimal. Both approaches have their trade-offs, so the choice depends on the problem constraints and your familiarity with the techniques. Great job following through. We've covered the problem regions cut by slashes, breaking it down into manageable parts and solving it using graph techniques. Remember, mastering problems like this will sharpen your algorithmic thinking. Thanks for joining, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!